So I wanted to share a few things about the exam itself before we got into the review overall. And so just kind of to remind you about a few things. This is a final exam given to us by the American Chemical Society. Its technical name is First Year Chemistry, First Term. That exam contains 70 multiple choice questions and has a 110-minute time limit. So for us, that is a slight difference in terms of what the schedule book says that our final exam length is. So if you go off the final exam schedule, it says that our exam is from 6 to 7:45. Well, because this exam is designed for those 5 extra minutes, you will receive those 5 extra minutes to take it. Now, one thing that I cannot give you that I did give you in the previous 2 exams, I cannot give you overtime on this exam. At the end of the 110 minutes, that is the end of the exam. So there will be no added extra time associated with this exam. When we hit the end, that's the end. You should know all of this information already. Our meeting from 2024, as opposed to here, there will be another final in this room. So if you show up here, you will not be given the correct final exam. So we're in room 224. The doors will open at 5:45. It's my hope that if we can get everybody to show up a little bit early, we can actually start right at 6 o'clock, as opposed to say 5 minutes after. If we end up starting a little bit late, that's okay as well. Does anybody have a 4 p.m. final? Okay, so that'll probably make things a little bit easier. I was going to say, if you did have a final that's running up right up against this, just let me know so that I can let you start potentially a little bit later. As far as allowed materials are concerned, there will be a periodic table in the exam booklet itself. So the exam itself is a bound booklet. You're not allowed to write in the exam booklet itself, but there is a periodic table inside the front cover of that booklet. And so that will be the periodic table that we use. We're not going to use the hard stock ones or any of the other ones we use this semester. We want to make sure that we're calculating molar masses correctly according to what the answer key is. So we got to use the one that they use as well. As far as calculators are concerned, they have to be non-graphing calculators. So any scientific calculator would work. Any algebraic calculator would work. If you don't have access to one of them. If you don't have access to one of those, couple of things. I have 3 calculators that I can give out to those who need it. They are Casio calculators. They are a little bit on the older side. So just kind of take that into consideration, especially if you've been working with the PI all this time. It's a little bit different. You can also borrow a calculator from the Learning Lab. That's another completely possible option. Or you can just borrow somebody else's. For the exam itself, you really just need the ability to add, subtract, multiply, and divide. So any calculator that does that, as long as it doesn't have a programmable graphing kind of component, is okay. If you've got a question about a calculator, just let me know. This is not in the official ACS required materials or allowed materials, but if we are kind of breaking that mold there, the equation sheet that you've been using all semester, the VSEPR and hybridization tables that you use with chapter 5 and exam 3, those will be given to you as well. And so what I'll do is I'll kind of print a split back to back, 1-page equation guide for you, and that will be the other thing that you're allowed. And then the last thing that we would give you give you scrap paper for your calculations, because again, you can't write in the exam book. So the exam itself, 70 multiple choice. It is a Scantron test. We will provide you the Scantron. So don't worry about having to go to the bookstore and try and figure out which green one's the right one or which blue one or whatever it is. We've got the right one that we want you to use. We will give it to you. Makes things a lot easier if you don't have to do it yourself. But because it is a Scantron, you are going to want to bring probably more than one pencil. There are pencil sharpeners in the room, but if you've got 2 or 3 pencils that are kind of available to you, that's less getting up for you in case you break a clip or something like that. So make sure you've got a couple of pencils with you, along with reasonably good eraser in case you make a mistake, and of course the calculator. Everything else will be provided. All right, any questions about the exam format, what's required, that kind of stuff? Okay. So exams make up 50% of your grade in total. The final exam is 150 points. You already have about 250 points of exams. So 150 out of 400, 3/8. So you're talking about somewhere around 18, 19. So that being said, again, it is scaled, and you already are carrying 10 bonus points in to the exam. So I've said this before, I'll say it again. You're just striving to do your best on this. You're going to be compared relative to not just the national sample, obviously scaled down, but also to your fellow classmates. So don't concern yourself with perfection, because you're not going to get it. Concern yourself rather with just doing as well as you can, knowing that if you perform close to how you performed on your other exams, you'll be good. has not been put into it yet. So, especially, with tonight's homework having those extra bonus points in it, that'll obviously lift up the grades a little bit as well. Patrick. Can't just start. Yeah, it's really about making sure that the marks are dark enough. So number 2 pencil, mechanical pencil should be good. Other questions before we get to more specific content kind of questions? Right. So as far as the exam is concerned, this mock exam that I gave you covers topically most of what you would expect to see. The only thing that's not covered in here is there's a good bit of thermochemistry on the final exam, and that's stuff you're not responsible for. When you come to those questions, just make a good stab at them. Yes, and if you're right, it boosts your grade. If you're wrong, it doesn't hurt your grade. But otherwise, what's in this review should be what you spend your time on. So really that's chapters 1 through 9. So those first 9 chapters of the book, that's where you should be focusing your study. And obviously you should be kind of considering, how much do you really need to study out of chapter 1, for example. Chapter 1 mostly is just kind of those fundamental definitions and unit conversion. Probably don't need to spend a whole lot of time on that. We've been doing unit conversion every chapter since. So, you may not necessarily know how many kilograms are in a pound, but then again, you're going to be given the information that you need to do that conversion anyway. Absolutely, completely out. Chapter 11 won't be there. Aside from, chapter 6, chapter 6 will be there for the most part. But really in just kind of basic ideas. Knowing the differences between the different air molecular forces, being able to make simple predictions on physical properties. There shouldn't be any phase diagrams. There shouldn't be any of that stuff that kind of ties back to chapter 1. So yeah, it's mostly chapters 1 through 9. Chapter 6, maybe just half chapter 6. That first day where we talk about the different types of air molecular forces. All right. So I asked you in advance to look at this mock final exam. We've got about half an hour. What kinds of questions do we want to go over? Where do we want to spend our time today? 19. All right. All right, this is good. This is a different question than what we had this morning. Which set of quantum numbers is correct and consistent with n equals 4? So what we have to remember is what do each of the quantum numbers mean. So remember, n basically gives us the energy level. L gives us the sublevel. M sub L gives us an orbital. And M sub S gives us the spin of an individual electron. So each successive quantum number gives us more and more specific information about the location of that electron and what that electron is doing. So with energy level 4, what we have to think about is, well, what goes into energy level 4? Remember, for every energy level, there are an equal number of sublevels. So that means that in the 4th energy level, there are 4 sublevels: the S, the P, the D, and the F. And so if you remember that L doesn't start at 1, it starts at 0. The S sublevel is 0, then 1, 2, 3 for D, for P, D, and F. So right away, we can eliminate option B, because option B implies the presence of a 5th sublevel. And we know that there are only 4 sublevels in that energy level. After that, we just have to kind of remember our rules. So when it comes to looking at the orbital level, remember the allowed values are from negative L to positive L. So we're bounded by L in that case. Well, we can eliminate option C then, because if L is equal to 2, M sub L can't be greater than. It has to be within the boundaries. 0 would be included. Because in counting that 0, that's what gives us the correct number of orbitals in that sublevel. So if I'm looking at the D sublevel, where I've got L is equal to 2. Well, remember the D sublevel has 5 orbitals in it. Those 5 orbitals, 2, 1, 0, -1, -2. So 0 is included in there. It's just the integer number line from positive to negative. Okay, so we've eliminated option C. Option A works. Option B works. Which one is correct? Well, remember, spin can either be positive half or negative half, dictating spin up or spin down. So this number is correct. This one can't be. Letter A is the correct answer. So questions that deal with quantum numbers, we have to remember, what do the quantum numbers tell us? And what are the boundaries of a given quantum number? And in most cases, the boundaries of a quantum number are related to the number that came before. The exception to that is, well, obviously the energy level doesn't have a quantum number before that. And the spin quantum number can only be 1 or 2 values, because there are only 2 possible electrons inside of that orbit. But this orbital is bounded by the sublevel. There are only certain values that are possible in a given energy. $22. All right, the fact that BCL, it should be BCL3. The fact that BCL3 is a planar molecule and NCl3 is pyramidal can be explained in a bunch of different ways, which is the best rationalization. Well, the way to go about it, we have to look at, we could try to reason our way through it. We could also just draw these out. And so with boron, we've got 3 valence electrons, and we've got 7 for each of the chlorines, so a total of 24. And so when we fill out the octet for all those chlorines, we can see that there's no remaining electrons around that boron. Now, our first instinct after that would be, well, we got to make a double bond or something like that so that boron doesn't lose its or acquires an octet. But remember, there are some exceptions to the octet rule, and those exceptions are always based on formal charge. See, the boron has only 3 valence electrons. With its 3 bonds, its formal charge is 0. So it's perfectly content right there, even though it doesn't have an octet. And so we see that in group 13. We also see it in group 2, where you can actually go under the octet rule if formal charge ends up zeroing out as a result. So that's the structure of the boron trichloride. For the nitrogen trichloride, we do the same thing. But remember, now we've got 5 for the nitrogen and 7 for each of the chlorines. We're going to have 26 here. So after the chlorines all fill out, there's still 2 electrons left for that nitrogen. So with a steric number of 3, our base shape here is trigonoplanar. With a steric number of 4, our base shape here is tetrahedral. And because of that lone pair of electrons, that tetrahedral gets condensed to trigonal pyramidal shape, or what they're calling pyramidal here. And so the answer here has everything to do with that center atom. And the center atom is the nitrogen compound having its own pair. Where the center atom, there's a lack of electrons on that center atom of the boron compound, means it's going to stay flat. All of the other statements, in some cases, they may be true. You know, letter A is true, but electronegativity has nothing to do with shape. It has everything, it deals with bond polarity, but not with shape. You know, letter C is correct as well. The size of the atom has nothing to do with the shape that it makes. Letter D is just flat out false. Backwards. Boron trichloride is the one that's at P2. The nitrogen trichloride is the one that's at P3. Again, it comes back to the steric number. Mason? So, in the cases of some of those kind of big historical kinds of experiments, what you would want to know is kind of what are the main conclusions from them. So, in the case of that Rutherford question, which is number 5, the Rutherford gold foil experiment really gave us 2 big ideas. The one big idea was those alpha particles shooting through that gold foil sample and not running into anything tells us that the atom is mostly in space. The other big idea that came out of the gold foil experiment was, if we're looking at the deflections, when those alpha particles actually hit something, they noted 2 things. One, we had big deflection. That tells us that there's something hard and massive in the middle. And we use the gold foil experiment to basically show that the nucleus exists. And the other thing is that when we had close encounters between the alpha particle and the nucleus, we noticed that the alpha particle was bending away. Well, that means that we know that the alpha particle is positively charged. That means that the nucleus is positively charged. So the Rutherford experiment gave us 2 ideas. First of all, discovers the nucleus. Second of all, tells us that the rest of the atom is basically empty space. Now we know that it's actually electrons. The electrons fill up that empty space, but relative to the size and mass of that nucleus, we also know that those electrons weigh practically nothing, which is why those alpha particles were able to punch through that gold foil and not run into anything along the way. So the other experiments that you could encounter, J.J. Thomson's cathode ray tube. Big takeaway from that is the discovery of the electron. And then the milk and oil drop experiment, where we uncovered the charge of the electron and therefore its mass, because the Thomson experiment also calculated the charge to mass ratio. So there are 3 things out of kind of that history of atomic theory that are important. Usually, I would say it's the Thomson experiment, the cathode ray, and the gold foil experiment that get picked on the most. Because in there you're talking about the discovery of the nucleus and the discovery of the electron. So you don't need to get too deep into kind of what the construction of the experiment was, like how they did it. It's more about what came about because of it. That's where you need to have the knowledge. What are the conclusions? Some other questions, Kate? Sure. Okay. 54, we are told we have 2 pure substances, A and B. They both melt at the same temperature. An unknown pure solid substance X also melts at that temperature. Melting points for mixtures of X with A X with B, and A with B are all done. And the melting point of each mixture is found to be below 87.5. What can we conclude based on this? Well, the concept here is freezing point depression. We know that if we have a mixture, the freezing point is going to come down. Or in this case, talking about the melting point, same thing. So, if I have a mixture, the freezing point, the melting point is going to come down as a result. Well, if X were A, or if X were B, then a mixture of X and A or X and B would yield no difference. Because if X is A and I combine X and A together, it's going to melt at 87.5 degrees because it's still a pure substance. It's all A. And similarly, if B were X, same thing. A mixture of B and X would melt at 87.5. And if A and B were the same thing. The fact that all three, when we test all their combinations with each other, all depress the freezing point, mean that they're all different. None of them is the same. So letter C is the correct answer. Because if X were either one of those A or B, we would know that. Because we would see one of the freezing points stay the same. They all went down. Understood. All right, we've got a CFC, fluorofluorocarbon. So we're talking about replacing one substance with another because the other one's environmental pollutant. What is most likely product if a molecule of this kind is bombarded with high energy, given the bond energy? Okay, so what we're being told here is we got a new compound, and its construction is going to be something along these lines. So we've got a bunch of carbon to fluorine bonds, we've got carbon to carbon bond, we've got carbon to fluorine bond, we've got carbon to hydrogen. The question is, if I blast this compound with energy, which bond's the least? Which bond is the most likely to break? And so we go to the bond energy and we can see, okay, hey, this one's the least. That's the least one. That's the bond that's going to break. So when I break this bond, what's left over? Well, I would have CF3, CHF, and I'd have CF. So the write-up of the problem sounds really complex. But what it comes down to is the bond strength. If I'm going to break a bond, the most likely bond to break is the weakest bond. And so when I break that bond, what happens to the? Victoria, you have a question? Okay. Okay. All right, I'm gonna pick on a couple in this, just because it's these problems are all kind of the same in terms of how to deal with them. So 39 is very similar to the calculations that you did with the formula in chapter 2. And all that you do in those is you turn the percent into grams, and then you turn the grams into moles, and then you do that mole comparison to figure out the empirical formula. So if we do that, we got 54 grams of sodium. We've got 8.5 grams of boron. We've got 37.5 grams of oxygen. More mass of sodium, 22.99. Boron is 10.81. Oxygen, we all know, is 16. So handling each of these individually, 54 divided by 22.99 will give us 2.35 moles. 8.5 divided by 10.81 will give us 0.786 moles. 37.5 divided by 16 will give us 2.34 moles. Okay. This is an important thing. This is a way to save yourself time on the exam. You can go and take this the rest of the way. But before you do, recognize something. Recognize that the sodium and the oxygen are exactly the same. The multiple choice test. Some of the answers are going to be those that don't have sodium and oxygen the same. If that's the case, eliminate them as options. Then it becomes a matter of a 3-to-1 ratio between oxygen and boron, or a 4-to-1 ratio. That's the difference between A and C. Now, if you can't look at that and see what it is, do that quick division. Divide this by 0.786 and get 3. And realize that A is the correct answer. Again, if you kind of think about that in your head, you say, okay, wait a second. 0.786, that's about 0.8. 4 times 8 is 32. That's not what we have. We don't have 3.2. We have 2.3. About 4. It must be 3. So any little thing that you can do to prevent you from having to punch in more numbers in your calculator is going to help a lot. So sometimes it is just a matter of logic, trying to figure out your way through the problem, logicking your way through it based upon things that you already think. The answer, there's nowhere in the instructions that says that you have to show your work for everything. So take advantage of the fact that they've given you answers and try to figure out which ones don't make any sense. And at the very least, you can't do the rest of it, you can at least kind of figure out, okay, I've got a 50-50 shot here. You know, that's a better guess than what I had before. For number 40, we've got iron 3 sulfate. We want to know the mass percent of oxygen Remember, for mass percent, we're talking about the mass of oxygen divided by the total mass of the whole thing times 100%. How many oxygens are in iron-free sulfate? Well, so we've got 12 oxygens in the numerator. And then in the denominator, we've got that same 12 oxygens, but we also have 2 irons and 3 sulfurs and those 12 oxygens in total. 12 times 16 gives us 192 as my mass of oxygen. If I add to that my 2 irons and my 3 sulfurs, I get nearly 400, 399.91. So 192 divided by 399.91 times 100%. Going to give me 48%. Right. The last little thing I'm going to share with you also comes out of this section. And it's question number 42. Right. In question number 42, it's another empirical molecular formula kind of question. It's just phrased up a little bit different. And I want to point out 2 things about this. One, you can handle 42 very similarly to the way that you did number 39, where you figure out the number of moles of carbon and hydrogen, and you determine the empirical formula. You just have to work it a little bit differently. Because what you need to do is you need to go from grams of water to to moles to moles of hydrogen, as opposed to just straight grams of moles. One extra step that you have to do in between. Now, test makers know this. And so they usually hide a really easy calculation in there to help you out. These 2 amounts of grams are directly related to the molar masses of the 2 compounds. 0.18 grams of water. Water is 18 grams per mole. 0.44 grams of carbon dioxide. Molar mass of carbon dioxide is 44 grams per mole. This is intentional. The reason they do this is because they know the calculation is kind of difficult. They're trying to make the math easier for you. And so if you go through the process, 0.18 grams divided by 18 grams per mole, you get 0.01 moles of water. And since there are 2 hydrogens in every water, we get 0.02 moles of hydrogen. 0.44 grams of carbon dioxide. Well, if I divide that by 44 grams per mole, I get 0.01 moles of carbon dioxide. And since every carbon dioxide has exactly 1 carbon in it, 0.01 moles of carbon. I can see here very easily, this is a 2-to-1 ratio. So my empirical formula is CH2. And so now I just need to find the molecular formula that matches with the empirical formula. If I don't see it immediately, I just start multiplying the formula by integers. So multiply it by 2. C2. One more time, just for fun. C2H4 would be the first possible, and that happens to be letter B. So I know we're out of time here. Thanks for your attention. Have a great weekend. Remember, 2 office hours starting 9 o'clock on Monday. Open review session in here starting at 2 o'clock Monday afternoon. Have a great weekend.